All right, everyone. Thank you for joining today. My name is Ryan Ingwerson from the National Renewable Energy Laboratory. I'll be the Zoom host for today's meeting. A couple quick tech things as we're letting people join today. First of all, I want to note that this meeting is being recorded and the recording will be made available as soon as possible after the event. We do have to do some things on our end to make that available, but we will get that up as soon as possible. Also want to note that everyone is joined in listen only mode. That means you will be muted throughout the presentation. We do very much welcome your questions and comments, so please put those in the chat and Q&A boxes and we will take a look at those and address them at the end of the presentation. And that's all for me. I will turn it over to our team of research scientists from NREL, Oak Ridge, and Matt Greaney at Clariant to take it away.
Great. Thank you so much. And thank you all for attending. We really appreciate the opportunity to share some of our thoughts about engineered catalyst design and forming. So to get started here, give you a little bit of a run of show. So we're going to talk about, what exactly is an engineered catalyst to kind of make sure that you're on the same page with the definitions that we have around this. Then Bruce is going to jump into a case study about FCC, as well as some considerations for technology selection and modeling. And then Matthew Greaney from Clariant is going to give an industrial perspective about catalyst forming and shaping. And I'll close things out here at the end of the presentation, talking about ways in which we're starting to think about engineered catalyst development in ChemCatBio. So to get us started, when we're talking about the engineered catalyst, and there's a number of different names for this, technical bodies, et cetera, but for the sake of this presentation, we'll call this an engineered catalyst. And so what we mean here is it's a multi-component catalyst formulation that possesses additives and other structural elements that are required for using these in an industrial commercial setting. And so these are additional considerations beyond your research powdered catalyst. So there are heat mass and heat transfer considerations, kind of functionality considerations, as well as mechanical considerations like strength, attrition resistance, for example. And then the idea is that simplified requirements for commercialization upon successful identification of promising research catalyst candidates. So if you're able to translate some of these important research elements into an engineered form, you've kind of simplified the process to get you to commercialization. You have an understanding of what elements impact your catalyst in a more commercial form. But that's non-trivial, right? So translation of synthesis methods from your bench scale, reactors testing and synthesis to multi-ton manufacture for commercial application is non-trivial. And the elements that are for consideration there, we'll get into a little bit. And then identification of an appropriate formulation. As I noted, that's a much more complex mixture of components that have physical and mechanical components, not just chemical considerations. And then shaping those powders into macroscopic forms has a lot of practical considerations. And so this is kind of the engineered catalyst as we start to think about it for the context of this presentation. And then we'll go ahead and jump into the case study by Bruce on FCC. So Bruce, take it away.
Okay, thank you, Fred. I hope you guys can hear me okay. Yeah, as Fred said, I decided to start this off with a case study, and the purpose of the case study is to illustrate, first of all, the strong interplay between the reactor technology that we're talking about, and then how kind of the consequences for designing and optimizing the engineered catalyst will continue to spill from that with time. And the case study that I picked is one that's near and dear to my heart, and it's FCC, fluid catalytic cracking. And I couldn't help but to start with a couple of gee whiz kind of pictures here, because some of these FCC units out there in the world are extremely large, and this is a particularly large one that's just coming online at the Dangote refinery in Nigeria. And what you're seeing here, guys, is just the regenerator for this big behemoth FCC unit, okay? And it's actually the largest, I think, object ever moved over African roads. And on the right picture, you can see it setting up in its more or less erected position. The narrow part at the bottom is where the bubbling bed is occurring, so where the catalyst is the coke is being combusted, and the big expanded region at the top is the freeboard or the disengagement zone, and you see all of the close coupled cyclones emanating or sticking out of the top of that big beast. So I thought that was a real eye-popping way to kind of bring that message home about just how big FCC is in today's modern world. Next slide, please. Now, what a lot of people don't really know, though, is that there was a bit of a technology race once catalytic cracking was discovered to actually come up with the technology that produced the winning solution, being FCC. Started in 1933 with the Houdry process and Eugene Houdry's patents. It was actually a fixed bed reactor. It had swing regeneration, and they used pelleted clay catalysts. Okay. And the next innovation on top of that, that was only a few years later, was thermophore or TCC. That was a moving bed system in which the catalyst pellets, they're still pellets, but they're actually moved between the reactor and the regenerators through bucket elevators. And as you can imagine, that could be kind of a clumsy process, and the thermal efficiency could leave something to be desired. Now, so the winner came out of the CRA consortium starting in 1942, which led to our modern FCC. That consortium was 5 oil companies, UOP, and some incredibly valuable guidance from MIT, 2 professors at MIT, who basically said, you know, if you make the particles small enough, they might be able to actually flow like a fluid. And with that concept, man, it was off to the races. Now you're talking about something that's a totally different animal. They started with crushed catalysts, but in 1946, very quickly made their way into spray-dried catalysts, which really was a game changer for controlling the physical properties and making the ideal engineered catalyst. 1960 zeolites were introduced. That was the second really big breakthrough. Today, just to give you an idea of the magnitude, you're talking about more than 400 units worldwide and over 10 million barrels a day of feeds processed. Next slide, please. So with such a big application, the FCC catalyst market, not surprisingly, is one of the biggest. It's about $3 billion a year, and that corresponds to roughly 1 million tons a year of catalyst. So all of those are made by spray dryers. So of course, the spray dryers that are used in FCC are big beasts in themselves. And I'm showing you here one on the left that I happen to know very, very well from my days with AkzoNobel and Albemarle. And on the right, you can see a younger version of myself actually sitting comfortably below the roof air distributor and right next to where the rotary atomizer would be. It's not actually there because that would be a massive safety hazard. So I basically photoshopped it in there to give you an idea. So that's where the slurry is atomized and meets the drying air in the top of this enormous drying chamber. Next slide, please. Okay, given that complexity, that means there's an awful lot of things that we end up studying to be able to make good FCC catalysts, good engineered catalysts in using this technology. On the right is a rotary atomizer that we had in our pilot plant where we were able to study atomization using high-speed video. And the important point here is the rheology of the slurries that are used to make FCC catalyst particles is extremely complex. Everything from viscoelasticity to thixotropy to Bingham fluids to you name it. It runs the gamut of the rheology. And you can see how that would strongly affect the formation of primary droplets, secondary droplets, ligament stretching, all kinds of things that can affect particle shape and particle integrity. On top of that, there's a lot of literature where people have looked at how the composition of the droplet being dried and the time temperature history can strongly affect the shape. And here's an oldie but a goodie that I've shown you from Charles Worth and Marshall in 1960, showing you how you can get all kinds of different shapes and particle integrities. The important thing is that spray drying in and of itself is a huge engineering exercise. And in the FCC world, when a new FCC catalyst is introduced, it's not surprising that it can take a lot of R&D to achieve good physical properties at commercial scale. And then one more slide, Fred, on FCC catalysts and this architecture. Architecture is a terminology that basically means how the particles are put together and what the void structure and the pore structure and everything else is in, and so how the whole thing works together in a colligative fashion. This example is from a good friend of mine, Elko Vogt. He published this in 2015. We actually worked together in AkzoNobel for many years, so he's very knowledgeable on this topic. It shows an FCC catalyst consisting of zeolite, clay, aluminum, silica, but there's actually a lot more. There are a much larger number of components in typical FCC catalysts than just these, and we don't have time to get into all the different flavors. Here in this paper, he's looking at things like on the left on some voidage that was identified inside some of those particles, and that's certainly something that's not ideal. And as a catalyst manufacturer, we'd like to engineer that out, but that can be tricky sometimes. On the left, he's showing how the the contaminants can accumulate in the particle, the nickel and vanadium, with exposure to the VGO or resid in this case. And all of these things come together to constitute the performance of the catalyst particle during its lifetime. And one term that we use frequently is accessibility, and that's kind of a catch-all term that basically says how well can molecules flow in and out of this catalyst particle and reach the right active sites. So next slide, please, Fred. So to step back up to a higher level, if we were to sit down and make a laundry list, okay, we've seen the FCC case and we see how deep and intricate that exercise turned into over the years. Obviously, we can't do all that in an ab initio fashion for deciding on a technology and engineered catalyst, but we can list some important considerations that we need to be keeping in mind. And I've only made a short list here because it would actually be a much longer list than this. The first is fluid solid hydrodynamics. And the second is interpellet mass transfer constraints. And by that, I actually mean the ratio of diffusion and reaction rates in something called the effectiveness factor. Now, these two I'm going to address in a couple of slides immediately following this. There are other things that are important, the deactivation rate, not just by coking, but of course by the irreversible deactivation from contaminants. And kind of connected to that as the regeneration requirement, how frequently, whatever, and then is the reaction endothermic, and do we need the energy from burning that coke like the FCC? That's what powers the endothermic cracking. Okay, that's an important consideration. And then things like heat integration, the intrapellet heat transfer for highly endothermic, exothermic reactions, also the interpellet heat transfer in between the pellets themselves and the bed and the wall and the reactor internals is important. Frequency, severity of coke oxidation regenerations, the effect of fast, large temperature swings on the physical integrity of the particles. Just the list goes on, but you can get an idea here of the things that, you know, we probably should be thinking about at a fairly early stage when we design a catalyst in a process. Next slide, please, Fred. So to say a little bit about the fluid solid hydrodynamics, I picked a couple of charts. This is something, of course, that's a very huge topic, and so we won't have time to go into it. On the left, I'm showing gas velocity divided by the minimum fluidization velocity on the y-axis, and it's plotted against the spherical equivalent particle diameter on the x-axis, and the curve showed different gas velocities over one order of magnitude. And basically, you can see clearly that as you go to smaller particles and higher gas velocities, you exceed the minimum fluidization velocity by orders of magnitude. That's what you want for something like a riser, where you really want dilute flow and very short residence time. And that's practiced today in today's modern short contact time FCC units. Now, the closer you get to that U over UMF equals 1, now you're talking about bubbling beds. Okay, so you're not transporting them at high velocities, but you are getting good gas solid mixing through the action of bubbling. And then once you get below that line of 1, we're basically in the regime of the fixed bed. Okay, we're not going to be able to move those particles. And so this is all very straightforward. We can decide how to design the catalyst properties such that, you know, it'll do what we want it to do in the process. Now, for fixed bed applications, we typically use something like the Ergun equation to predict the pressure drop. And here I'm showing the same kind of plot. You're showing the logarithmic particle diameter on the x-axis and the specific pressure drop, pascals per meter, on the y-axis. Of course, as the gas velocity goes up, the pressure drop goes up. And of course, as the particle size gets smaller, the pressure drop goes up because the voids between the particles are becoming much, much smaller. And the viscous drag is increasing dramatically in this case. Now, these can indeed have velocities that are well above UMF, but they can still be fixed bed applications because, for one thing, they could be downflow, and then you don't have any fluidization, or you could simply constrain the catalyst by locking it into the fixed bed by the vessel itself. So this is all very straightforward engineering, very well understood, but something that needs to be applied very rigorously when we design the engineered catalyst. Okay, next slide is on effectiveness factor. Now, this is a concept that's been around for a long time, since the 40s and 50s, actually. It's basically that there is a ratio of the overall actual rate of reaction divided by the rate of reaction that would exist if all the catalyst surface area saw the bulk composition and temperature. All right, so it's the effect of the diffusion on shutting down or slowing down our reaction. It's typically plotted against the Thiele modulus. I show you on the bottom there, that's a function of the reaction order. It's basically ratio of reaction rate to diffusion. And the particle size is an important parameter. And there's been tons of stuff. There's the engineering literature is replete with all of these different types of effectiveness factor models. I actually wrote a review article in September 1, 1986, where I actually summarized about 3 dozen of these models, and there's a lot more since then. It's not a dead subject, though. Here's a paper I'm showing right below that was authored by some of my colleagues at NREL, which is a very innovative paper where they actually use some very advanced mathematics to look at multi-step reactions and develop something called the multi-step effectiveness vector. So it's by no means a dead subject, but it is important to know the more complicated we get, the more difficult it is to derive analytical expressions, and that's where the combined pellet reactor modeling steps in and really takes over at that point. And that helps me segue, next slide, Fred, into the last part of my presentation, which is how we can couple computational modeling and experimental design in ways that can help us expedite the process of designing catalysts and moving them through the normal sequence of lab to pilot to large pilot to commercial. Okay, this work basically is something that goes on under the auspices of the Consortium for Computational Physics and Chemistry, of which I'm a member. It's a consortium of 6 national labs where we have atomic scale modeling, mesoscale modeling, and then of course reactor scale modeling, which is the kind of thing that I do primarily. And I do some particle modeling in my CCPC work, but it's not at the same level of detail as our mesoscale modelers. It's enough basically to bring the right effects and fold them into the reactor scale effects. Next slide, Fred. And I did want to point out that there's a couple of, if you're interested in this approach, there are a couple of resources that are on the web. These are basically related to a DFO program that we ran in 2021, 2022. That's a direct funded opportunity. We did a webinar on October 20th of last year in which the 3 main principals, CTO, CEO of 3 private companies, basically gave testimonies of how the CCPC's computational approach helped them move their technologies up in scale in an accelerated fashion. And so if you're really interested, by all means, dig into that. There's also an e-blast specific to Pyran, one of the companies, where we basically document how we helped them achieve a 1000x scale up in a single step, which is not something that we would recommend, but they had a very aggressive timetable and we were able to help them pull it off. And you can find that also on the web. Next slide. So what we've done is to come up with an idealized approach for combining computation and experiment, and the objective being to produce computational scale-up models that are really useful for moving to pilot scale. And it starts with things like intrinsic kinetics, and then it folds in the effect of formulating and forming, and which we can ideally study with single or a few pellets with small gradients. Then you start folding in bed effects, and this of course is for a fixed bed application where you look at the heat transfer. You can also look at mass transfer, axial radial dispersion, things like that. And the end result from that is to move into a pre-pilot reactor, which we are currently in the process of building at Oak Ridge National Lab, which is designed for 100 grams of catalyst, and it's designed in such a way that we can combine it with modeling, specific modeling, to address all of these individual components of the overall framework, with the objective, again, to build a scale-up model that can be used to increase the speed of moving to pilot scale. And this is work that's ongoing right now at Oak Ridge National Lab. And I'm going to end with next slide, Fred. Just some illustrations that there are a number of novel applications out there. These are just 3 that I picked of many for looking at the effect of, like in the top with the Timken reactor, looking at the effect of the formulating of that catalyst into a certain type of particle. There's an analog that involves a stirred tank reactor, which basically isolates individual catalyst pills And there's a lot of these things that are basically designed at estimating or quantifying the heat transfer effects to give us those parameters we need to do this kind of modeling. And with that, I know that was a lot of information in a short time frame, but I think it's time for me to turn it back over, Fred. Will that be to you or maybe directly to Matt?
That's great. Thanks, Bruce. Really appreciate that.
Yeah.
Okay, Greaney, you're all set. I think you're muted.
Okay, hopefully you can hear me.
Thanks, Matt.
All right, thanks. So the work I do at Clariant is very applied R&D, which means that probably just, I'd say you can pretty much describe it as working on improving existing catalysts. So, you know, maybe some smaller tweaks. We want to improve certain performance metrics or reduce cost of production, et cetera, or developing new catalysts for primarily existing market applications. And so whether we're improving an existing catalyst or developing a brand new type of catalyst, the way I like to look at the challenge is somewhat summarized in this Venn diagram. And so initially, you know, a lot of us are thinking what's in the catalyst. I describe it as this upper circle that encompasses all the catalyst composition. So this is basically the elemental composition of the catalyst. And that's very important. And a lot of us are familiar with exploring this space. However, that's far from the only concern, especially in the work that we do at Clariant R&D. And so the other circles in this Venn diagram are capturing some of the things that aren't necessarily always considered when you're developing a new catalyst in the lab. But this is very heavily tied to the concept of engineering a catalyst or the engineered catalyst. So this red circle really, in my opinion, describes a lot of what goes into engineering a catalyst, and I call this the catalyst processing history. And so we can have the same composition 1,000 times and put it together differently 1,000 times, and maybe one of those examples or one of those samples is going to be the hit, the one that works. And so how do we put things together, whether we mix or impregnate or precipitate? This is how the catalyst is made. But then when we get into engineering the catalyst, it goes into a lot of what Fred and Bruce touched on earlier. And this is the use of additives and lubricants and burnouts and pore formers, et cetera. And then we incorporate this more complicated blend of components to facilitate forming and shaping and sizing of the catalyst. And then, of course, there's typically a thermal treatment that goes along with that. And then importantly, how do we decide how we want to engineer the catalyst? Well, that's very strongly linked to the third circle, the green circle in this Venn diagram, which I describe as the reactor process conditions. And so how are we going to utilize this catalyst? What type of reactor, scale, dimensions, lots of considerations. One of the very important considerations is the pressure drop that needs to be, that the reactor is designed to accommodate. And so how do we control the pressure drop? It really goes into how do we engineer the catalyst? How do we put it all together? And then, of course, at the very foundation of the catalyst, it's everything that's in the catalyst. So next slide, please. So considering catalyst form factors, Bruce touched on several of these topics, and I will follow up on that. And so how do we know how we want to engineer the catalyst? Do we want a small sphere? Do we want to extrudate? Do we want a more complex shaped catalyst? So a lot of this will be determined by the scale of the reactor. And so how is that reactor loaded? How efficiently do we need to pack those catalysts in there? That'll very strongly affect the pressure drop that is experienced from the top to the bottom of that reactor or that catalyst bed. Mechanical strength is a very important attribute for these catalysts. So we can't load in full particle catalysts and have them fall apart into powder very quickly. That causes problems with pressure drop and performance issues. You know, we need to, a lot of times there's a thermal profile that needs to be managed. Bruce mentioned the endothermic nature of STC process that's fueled by coke burn. Sometimes there's very exothermic processes that are also can be problematic. And so the reactor needs to be designed and the catalyst needs to be engineered such that you can control the thermal profile in your reactor bed to get the target performance that you're going after. There's different types of reactors. Bruce also touched on this, whether it's fixed fluidized moving bed, et cetera, that also has a very strong impact or influence on how you decide what shape, size, and mechanical properties your engineered catalyst needs. What type of phases of matter are present in your reactor, right? Are we talking a single phase or multi-phase systems? Gas phase is a very common type of reactor. I'd say probably the most common, but that's not necessarily true especially for a lot of newer trends and technologies. And then finally, there's always a practical aspect of this. We are a for-profit private company, and we, need to make money, right? So the way that we make the catalyst and engineer it and use it has to be economically viable. And we have to be able to produce the catalyst at a reasonable cost. And then finally, there's a scale and throughput consideration. Bruce showed this pretty impressive picture of this massive FCC regenerator. That's a lot of catalyst. I think he said 1 million tons of catalyst a year, right? So you have to be able to make this stuff. So we can't make the catalyst, we can't engineer it to such a complicated state that it's too slow to make and we can't keep up with the demand. So all these things are really need to be considered. I wouldn't say one's more important than the other, but it's kind of all inclusive in order to figure out how are we going to engineer the catalyst and what are we going to make. Next slide, please. So at Clariant, we make a lot of catalysts for many different types of applications. And this slide is just showing kind of the breadth of those applications, right? From ammonia and methanol synthesis to emission controls, petrochemicals, a big one for us. All of these applications have unique catalysts, and most of the catalysts have unique engineered properties to meet the requirements for each one of these applications, and using some of the considerations I just covered in the previous slide. Next slide, please. All right, and this is I think it's a kind of informative picture of, 8 different classes or fields of application here, and these are actual catalyst pictures for each one of those applications. And so in the upper left, this is a dehydrogenation catalyst. It's green. It's a pretty simple looking cylinder. It has a similar shape as the catalyst in the lower left that has a fuels application. But then if we move one panel to the right, now if we look at this emission control, oxidation, and zeolite catalyst, this is a pretty complicated monolith, right? So now this is a totally different form factor than the dehydrogenation or fuels application. But the reason that we've engineered the catalyst to have, it's not because this is easier to make, it's because this is meeting the needs for the specific application. And then you can look at some of the other pictures. You see on the upper right, styrene and MTP catalyst. It has this kind of extruded star shape, right? So there's a lot of consideration in the pressure drop, and this specific shape allows you to operate the catalyst under conditions that would not necessarily be optimal or desirable if we just had a simple cylinder, right? And then I think the lower right is a nice picture where we have this 7-hole honeycomb, right? And so now there's a lot of this is not the simplest shape to make. Actually, it's 8 holes. There's a big hole in the middle, but that specific engineered shape is allowing us to operate again under the conditions necessary to yield the target performance. Next slide. So just a couple examples of different looking catalysts or different looking engineered catalysts for specific applications. And so this one is for DNOx, so selective catalytic reduction. And so this is again, I showed in the previous slide one of these monoliths, but this I guess it's beige box, right? We can design it differently, but there's a lot of different parameters that we can tune on these monoliths. At the end of the day, they're going to be dip coated or wash coated with active metals. So the active metal will be supported on this monolith. Why do we need this complicated structure? Well, this is a fixed bed configuration. It has a very high space velocity, so very high flows. So we need to get a lot of contact with our reactants and our active surface, and there's no recycle, right? So if this is an emission control, right? Say just consider, a diesel truck, right? We're not recycling that exhaust, right? So we need to effectively and efficiently conduct the SCR through this limited length monolith And so then we end up getting this more complex kind of engineered, I guess it's a very high surface area, but lots of these little screens are, high mesh type material. Next slide, please. Here's an example for using vanadium phosphates for maleic anhydride production. On the upper left, you see two different shaped catalysts. There's this, on the far upper left, you have this cylinder with a hole in the middle. Looks kind of like a noodle. And then right below it, you have a more complex shape, right? So it still has this hole down the center, but now you have this kind of ribbed perimeter. And these, again, are not the simplest shapes to make, but depending on the type of reactor this is going into and the specifications for the application, we need to pick one or the other shape, and we have additional shapes, right? These are proprietary engineered shapes for achieving, again, target performance in different types of reactors, right? And so we're not building all these reactors identical across the world. They have different ages, right? So older reactors might have cruder technology, newer technology might be a little bit more complicated, but allows you to get a higher level performance. And so in this specific application, it's a fixed bed system or fixed bed configuration, but we have thousands of small reactor tubes in parallel because this is a very exothermic reaction, and without controlling that thermal profile, you can quickly get runaway. And so this, again, the engineering of the catalyst has to consider all the end applications that the catalyst is going to be used for. And in this specific case, we're very sensitive to space velocity, and like I said, the thermal management is critical. And so these kind of unique shapes allow you to operate under what are fairly aggressive conditions, I would say. This catalyst is extruded and calcined, and then, like I said, the shape is dictated by the reactor. One more slide. All right, and this is the final slide I'll cover. Again, another example of what I would say is a fairly simple shaped or engineered catalyst. Should be careful saying that, but obviously there's a lot of complexity in the systems. But of the three examples I'm covering, this is, I would say, the easiest catalyst to engineer and make. It's simple. It's a simple extruded cylinder. Why is it so simple? Well, because the dehydrogenation technology that this catalyst is intended for is massive, right? It's not the FCC level massive, but it's pretty big, right? So on the lower picture here, the lower left picture, that's one of our CATOFIN plants, and there are 10 parallel reactors. So these kind of tubes all in a line in the middle of that stack, those are all reactors that contain a couple hundred tons each of this catalyst. So we're making this catalyst more than 10,000 tons a year. Again, so I mentioned something about the throughput. We can't, it's more challenging to make the more complex catalysts. And so if we have to make a large amount of the catalyst, then we need to have something that we can realistically meet that demand with our throughput capabilities. This is an alumina-based catalyst. We form and extrude it, calcine it, and then impregnate. Sometimes we'll add something called texture or some other additives, that more complex level of ingredients that Fred covered on the first slide. This could be to adjust the porosity or the surface area, or target or mechanical strength, or all of the above. But the key thing for this application is, as simple as this looks, there are still unique specific considerations that need to go into making this catalyst or forming this catalyst. So we simply impregnate some chromium on this catalyst and a couple other promoters, but the carrier physical properties are key to the long-term stability and performance of this catalyst. And like I mentioned or wrote down in this bullet point, this fourth bullet up on the top there, this catalyst has to operate for over 4 years. And so it's great if it works for a couple months, but if it starts to lose its activity or target performance, we lose the customer. And so all of these considerations are key for us to staying in business, maintaining a good reputation, and putting out a good product. Thank you very much.
Thanks, Matt. Really appreciate that. Okay, to close us out here, I won't belabor this point. I think the last two speakers have done a really good job kind of impressing upon you the challenges that are associated in going from your simple traditional research catalyst where you just have an active phase and a support to this more complex mixture that it is required to have a lot of different components to meet those mechanical and structural components. So this is a research area in its own, and obviously something that is extremely important to focus on should you be targeting commercialization of a process. And so I'm going to talk to you a little bit about what we've done both in collaboration with ChemCatBio and activities within ChemCatBio associated with how we're starting to think about this in the consortium. And so what we had done initially with some prior work was establish an industrial advisory board associated with starting to understand some of these considerations and focus on which ones are important for us to consider in the national lab setting. We had a number of catalyst targets. So we had a platinum on titanium material and a copper H-beta material for two separate projects within the ChemCatBio consortium that we selected as initial targets. So can we start to consider engineered catalysts and synthesize some of these materials in-house to start reducing the risks associated with these materials? When we start to include these more complex mixtures, there are some potentially unintended consequences on the performance of those materials. And so we wanted to start addressing those concerns in the near term. We worked with these projects to establish what the physicochemical property requirements are for these systems, what the process and reactor configurations were. And then we sought industrial expert input and review, selected the equipment that was necessary for this with industrial guidance so that we could start to make some minimum viable engineered catalyst materials. We assessed best practices, again, working with our industrial partners and the patent literature and the academic literature to determine best ways that we can start to approach this project within the consortium, and then develop these methods and work with industrial guidance to kind of down select what we should be working on, how we should be doing it. And then we produced our first engineered catalyst. So this is a kind of the structure that we took at the onset of efforts around engineered catalysts, both within and closely tied to the ChemCatBio consortium. And the reason that we're starting to consider all this is that there's a really robust catalyst development cycle within ChemCatBio. There's new materials discovery, performance evaluation. These are all structured in a way that there's down select and go no-go decision points. And ultimately, the hope is that a lot of this goes to material and application IP. So we're generating IP for high performance materials for a number of different pathways, conversion pathways within ChemCatBio. And what we're starting to think about is how do we start to de-risk these catalysts and develop technology transfer packages associated with engineered forms. So we're really looking here at this first stage technical body where we're making hundreds of grams of material using industry standard methods and industry standard equipment to start to reduce the risk associated with the manufacture of these materials, because we're not going to manufacture these within ChemCatBio, but we need to know that they can be done, and we need to know what challenges a chemical manufacturer might run into when doing this. And so we're really starting to try to consider this baseline engineered catalyst form. And then what we did was, again, looked at all of the different materials that we would need to be manufacturing and the process steps associated with those, while keeping paying very close attention to make sure that these were done in ways that there were industrial analogs. And so looking at high shear mixers and orbital mixers, screw extruders, rotary and muffle furnaces that can operate both in batch or continuous flow modes, and then bucket mixers and cement mixers for tumbling and calcining and simulating attrition within the manufacturing process. And so we commissioned this in-house equipment for preparing 1 to 10 kilogram scale catalyst manufacturing, which gives us the ability to optimize the translation between that research material and these formed catalysts. And we've done this in a way under the guidance of industrial partners that the knowledge that we're generating within this type of paradigm is something that could be transferred to an industrial partner for commercialization. The steps are there, the materials considerations associated with purities and powders that we're using are all informed by that industrial advisory board. And so we can really translate this knowledge to commercial practice. And so we can also use this as a pipeline within our existing technologies, right? So we've got new materials that we're developing all day. We're doing that. We're generating IP. We're creating new materials. And we can start to consider ways in which we can incorporate those into commercial form. So one example, which is under review right now, is this flame spray pyrolysis method to make your catalyst and support in a single step, and then you can extrude this into a commercial material. So I'll leave this summary slide up for anybody to ask any questions, but effectively what we have here is an industrial guided engineering engineering scale catalyst synthesis capability developed within BITO funded resources and put to bear within ChemCatBio's problems are associated with catalyst risk and commercialization. And so I think in the interest of time, I'll stop there. And I think, Ryan, I'm going to hand it over to you and we're going to field some questions. Is that right?
Yeah, it looks like we did have a couple questions that got answered already. One that just came in. Two-part question. First one, how does CCB determine which transformations are highest priority for catalyst development?
So ChemCatBio has a pretty robust development cycle. We are obviously funded by Bioenergy Technologies Office. And so, these are ideas that are pitched within the consortium, ideas that have been refined within the consortium, and then we work with DOE to prioritize pathways and catalysts. And then the principal investigators of the different pathways and projects do internal evaluations of what systems are either ready for manufacture to look at de-risking or where they're still in kind of lower TRL evaluation and try to understand just the fundamental chemistry associated with that process. So there's a number of different ways in which that type of down selection prioritization occurs, and largely it depends on the project and what stage that project is in.
Great, thank you. And then the second part to that is just wondering if there is a point of contact for someone at CCB to describe a transformation that could be impactful based on downstream work from the targeted molecules.
So ChemCatBio, we have a pretty singular point of contact. So Dan Ruddy and Josh Scheidley are the director and co-director of ChemCatBio, and they are happy to field questions associated with anticipated processes or anything of that nature. So you can access all of the information, all of the point of contacts at chemcatbio.org. You can see the leadership structure there, and there's forums in which you can contact us, or you can contact the leadership of ChemCatBio directly through that forum.
All right. Looks like that's all the questions we have. Give people another second here just in case. All right, I think that's all we've got.
Great.
All right, thank you everyone for joining. Have a wonderful day.
Thanks all. Take care.